Hello everyone, welcome to the YouTube channel Simply Solve. This is Kushan. This is the third video of the tutorial series where we are deriving various expressions in electrostatics. Again, if you have any query, do comment in the comment section. Also subscribe to the channel for more videos. Now in this tutorial, we are going to learn the general expression for electric field due to dipole. So it is a general case, that means a case which is other than the axial line and the equatorial line. So see here, the point P is neither on the axial line of the dipole nor it is located in the equatorial line of the dipole. So let's get started. So this is considering this as a short dipole. So first consider this AB a short dipole. For short dipole, and we know the assumption behind this short dipole. So for short dipole, we know that this 2a is much less than r, as we did in our previous videos. So what is 2a? 2a is the distance of separation between these two charges, charge at point A and charge at point B. This distance of separation between these two charges is nothing else than 2a. And r is the distance of the point of observation or the point of interest from the center of the dipole. Now, so initially, first condition over here, we will divide the vector p, that is the dipole moment, into two components. One is its cos component. So let us consider that dipole moment. We know that dipole moment always acts from negative charge towards a positive charge. So this is the dipole moment p, right? And so this becomes the cos component p cos theta, this one, and this becomes the sine component, that is p sine theta, right? Now we will first consider the magnitude of the electric field at this point p due to the cos component of the dipole moment and the sine component of the dipole moment. So first let us consider E1 is the electric field due to the cos component of the dipole. So see, so the magnitude can be determined by the general expression for electric field due to dipole on its axial point. See why I am using this case, because if we consider this p cos theta, if we consider this p cos theta dipole or the p cos theta component, it is in the axial line with that of the point P, point of observation. So we will be using the formula for electric field due to dipole on the axial line. So it becomes 1 by 4 pi epsilon naught. So the formula was 2p by r cube. Here it will be 2p cos theta, right? Since the dipole moment is 2p cos theta, so 2p by r cube. Now the direction, so as we know that for axial line, as we also derived earlier, so direction of the electric field is in the same direction as that of the dipole. So this becomes E1 and the direction is like this, right? Now we will calculate the magnitude for dipole due to the sine component, so E2, right? See, if this is the sine component of the dipole moment and our point of observation is point P, right? Point of observation is point P. So this dipole and this point are perpendicular to each other. In other words, we can say that this point P is in the equatorial line with respect to the sine component of the dipole moment, right? P sine theta. So hence we will use the formula for equatorial position. So 1 by 4 pi epsilon naught, and that was p by r cube. The formula was p by r cube. So here it becomes p sine theta. So p sine theta by r cube. Now there is a elaborate detailed description or explanation in our previous video where I said how the direction, what is the direction of the electric field when the point of observation is an equatorial position, right? So since here it is an equatorial position, see, we found out there, and we are using that case, that the electric field will be in the direction opposite to the dipole moment. See here, the dipole moment is in this direction, in the direction of p sine theta, right? And that is why the electric field due to the dipole in the equatorial position will be in the direction exactly opposite to that of the dipole. Here the dipole is p sine theta, right? So we are done with the direction as well as magnitude of the both electric field. Again, we need to note that the angle between this vector E1, right, between this vector E1 and this vector E2, angle is 90 degree, because here the cos component and the sine component was at an angle of obviously 90 degree, right. So now we will calculate the resultant electric field at the point P. So we will be using the basic formula for vector, that is if two vectors are A and B, so we can find the resultant vector by using this formula, yeah, just like that. But theta is the angle of separation between the two vectors A and B. So we will be using this formula. So the resultant electric field E is equal to E1 square plus E2 square plus 2 E1 E2, and just now what I said, this theta is nothing other than 90 degree, right, since here the cos component and sine component are at an angle of 90 degree. So 2 E1 E2 cos 90, and we know cos 90 is nothing other than 0, right, and obviously there was half out there, right. So we are left with, implies E is equal to E1 square plus E2 square whole square, sorry, to the power half, right, since this part becomes 0. So we will directly put these values over here. So becomes 1 by 4 pi epsilon naught 2p cos theta by r cube, and this square, so it becomes E1 square plus 1 by 4 pi epsilon naught, right, and it is p sine theta, right, p sine theta by r cube, and again square, and we are left with to the power half outside, right. So we can take this out, so it becomes 1 by 4 pi epsilon naught can be taken outside of the square root, even this p by r cube can also be taken outside, p by r cube. So we are left with under root, within the root is 2 cos theta whole square plus sine square theta, which becomes like 1 by 4 pi epsilon naught p by r cube under root 4 cos square theta plus sine square theta, right. So we know cos square theta plus sine square theta is equal to 1, so we can write the final value as 1 by 4 pi epsilon naught, right, p by r cube remains same under root 3 cos square theta plus 1 sine square theta plus cos square theta becomes 1, and we are left with this. So this is the final expression for the magnitude of electric field at some any generalized position, right, for some generalized position, any point other than the equatorial position or the axial position. Now comes the direction. So what will be the direction? Again, in our previous video we found out a way of calculating direction, nothing other than the general case for calculation of direction. So like that, so we found out like tan alpha is equal to b sine theta by a plus b cos theta. So this was the basic formula, right? So this is for general case. So in our case we can use this formula tan alpha. So which is alpha? So this one, this angle becomes our alpha. This angle is our alpha, right? So tan alpha will be equal to, see, in our case we don't need to calculate all these things, since this is 90 degree, since it is 90 degree, tan alpha can be written down easily as E2 by E1, like that directly, since it is 90 degree, and E2 by E1 from the concept of trigonometry. So it becomes E2 by E1, and this becomes, so E2, so we'll put the value, right? It becomes 1 by 4 pi epsilon naught, right? P sine theta by r cube whole divided by E1, that is 1 by 4 pi epsilon naught, P, it will be 2p cos theta by r cube. So this r cube gets cancelled, this entire thing gets cancelled, this p gets cancelled, and we are left with half tan theta. Therefore the direction, I am writing over here, so the direction alpha will be tan inverse half tan theta. That's it. So again we come to the conclusion with the final expression being this 1 by 4 pi epsilon naught p by r cube under root 3 cos square theta plus 1, and the direction is tan inverse into half tan theta. So I think that's all for today, and I will put in the description box the link to the Quora where I have performed this derivation, so you can follow it over there also. Again, if you have any query, feel free to comment in the comment section. Also subscribe to the channel for more videos. Thank you.